Good morning, everyone. This is 7.6 for trigonometry, Math 154 at College of the Sequoias for spring 2020. We are on our stay home, shelter at home lockdown from the coronavirus. 7.6 is on trigonometric equations. So let's discuss that a little bit. Get the center where I want it. Trigonometric equations. Before we start covering the trig equations, let's flash back to what we know from algebra. Algebra, we had linear equations. Linear equations were kind of like 2 times x plus 1 equals 3 times x minus 6 plus 5, something like that. Single variable, exponents to the first power. We could have two variables, they still make a line, like y equals x is a line. Then we had quadratic equations. But right now we're just looking at equations where there's no y variable. Quadratic equations, something like x squared plus 4x plus 4. This was anything of the form ax squared plus bx plus c equals 0. And in both of these equations, types of equations, the way we went about solving them, solving these equations involved isolating the variable. Require isolating the variable. For the linear equations, this required doing stuff like distributing, gathering x's on one side, constants on the other. Etc. You're quite familiar with that, I hope. For the quadratic equations, we had a couple approaches we could do. We could use the zero product rule. And that said, if a times b equals 0, then a equals 0 or b equals 0. And the way we use that there is we factored the equation. And set each term equal to 0. We also had the option of using the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. I think factoring is the quicker way to go if you recognize the factors. If you don't recognize the factors, it's not helpful. And I'll leave this up here for a second. Hit pause so you can take down what you need. Okay. The other option we had, if there were radical signs, we would square to clear a square root. That kind of idea. But this had the potential to introduce extraneous solutions. Or the bad juju solutions. You don't want bad juju. That's what we did in algebra. In trigonometry, yeah, well, for any of these equations, these setups, linear or quadratic, I could replace the variable with a trig function. And the solution was much the same. Just as we solved for x, we will now solve for the trig function. And then we have to take it a step further, find all angles that satisfy that result. When you're ready, we'll take a look at some examples. Okay. Actually, let's go to another page. You ready? Tell me, are you ready? So here we will okay, so example. 2 cosine theta plus 1 equals 0. And for part A, we'll find solutions on the interval 0 to 2 pi. And B, all solutions. Okay, so I'm going to treat cosine theta like x. When we'd solve linear equations, we'd subtract the constant to the other side. We divide by the coefficient. And I get cosine theta equals -1/2. So part A, where does that occur in 0 to 2 pi? When cosine theta equals 1/2, we have a reference angle of 60 degrees or pi over 3. And we're looking at cosine is negative in quadrants 2 and 3. So we're looking at a reference angle of 60 degrees there, or pi over 3, and we're looking at pi over 3 here. So I know from 0 to here, or 0 all the way down is pi. I subtract pi over 3. Let's call theta 1, or the reference angle 1. Sorry. Reference angle 1 will be that one. Theta 1 is 2 pi over 3, or 120 degrees. And when I add pi over 3, if I go all the way around to this one, we'll call that theta 2. Theta 2 is now 4 pi over 3, or 240 degrees. That answered A. For part B, I want all solutions, which means I can take extra laps around. Which means theta 1 can be 2 pi over 3 plus any multiple of 2 pi. So 2 pi n, where n is an integer. Or we could do 120 degrees plus 360 degrees n if we wanted n degrees. Theta 2, 4 pi over 3, also with 2 pi over n. And this is 240 degrees plus multiples of 360. And again, n is in the integer. That's kind of what we're doing here. Let's take a look at some more. So I've got cosine theta, tangent theta equals cosine theta. You might be inclined to divide by cosine theta. Let's see what happens if you do. If we divide by cosine theta, I get tangent theta equals 1. And we know that happens at pi over 4 and 5 pi over 4. Which is basically pi over 4 plus pi n for any loop around. Now, what happens if we move the cosine to the other side? Another approach. If I move cosine theta from the right by subtraction to the left, I have that. I can factor out cosine theta. I'm left with tangent theta minus 1 equals 0. And now I've got two things that multiply to make 0. This is a zero product rule. This tells me cosine theta equals 0, or tangent theta minus 1 equals 0. Now I add the 1 to the other side, and that led me to the solutions I had before. Theta equals pi over 4 plus n pi, or pi n, however you want to write it. And those are still part of the solution. Notice, though, that when we divided by cosine theta, we lost this solution. What satisfies that? Where does cosine theta equal 0? Well, that happens at pi over 2 and 3 pi over 2. And if we keep going laps around, this is pi over 2 plus n pi. Those are also valid solutions. Do they work in the original equation? Let's just verify that. Because pi over 2 is not in this category. Let's just check pi over 2. We had cosine theta, tangent theta equals cosine theta. And I get cosine pi over 2, tangent pi over 2 equals cosine pi over 2. And these are both 0. We got 0 equals 0. Those are valid solutions. By eliminating them, we actually broke the system. So you do not want to divide out a trigonometry function. So moral, don't divide out trigonometry functions. You lose potential solutions. All right, ready for more? What else we got here? Those were some linear ones, kind of quadratic. That last one was a little quadratic because we had to factor. Let's take a look at an actual quadratic function. Tangent squared x minus tangent x minus 2 equals 0. Now, this might help you. If we make a substitution, let's say u equals tangent x. You'll do this a lot in calculus. It's good to practice doing it now. Then this becomes u squared minus u minus 2 equals 0. Which factors? When I factor it, I've got u minus 2 times u plus 1 equals 0. And I can actually stick tangent x back in. Tangent x minus 2 times tangent x plus 1 equals 0. And we'll set each term equal to 0. Tangent x minus 2 equals 0. Or tangent x plus 1 equals 0. And we get tangent x equals 2. Or tangent x equals -1. We know the values for when tangent x equals 1 or -1. Those are on the diagonals. The negative ones, this is when x equals 3 pi over 4, 7 pi over 4. You can keep doing laps around. 3 pi over 4 plus n pi. Where tangent x equals 2, though, I'm not really sure. This is where our inverse functions come in. We'll say x equals tangent inverse 2. Tangent inverse of 2. And I get x equals 1.107. And where is that going to occur? Tangent inverse goes from negative pi over 2 to pi over 2. This is a positive one. It's right there. Does this angle over here work? So that's 1.107. Does that one work? That's 1.107 plus pi. Let's take a look. Does that inverse function mess things up? I'm going to add pi to this answer. And now I'm going to take tangent of my answer and see if I get 2. I do. So when we're using inverses, it just helps us find this one, but then check to see if we can wrap it around again over here, because the 2 should be another 180 as well. It's the same reference angle. So I could have 11 or 1.107, and I could go around another pi, and I could keep going around pi. So this will be plus n pi. Good stuff? You ready for more? All right, yeah, woohoo! Let's do it. All right. Let's have sine x times sine x plus 2 equals -1. So what happens here? We distribute. We have sine squared x plus 2 sine x. And I'm going to add the 1 over. So I get plus 1 equals 0. last time we factored, this one factors. Let's just take a look at treating this as a quadratic equation. If I say u equals sine x, this is u squared plus 2u plus 1 equals 0. And it should be easy to see that it factors. But let's just practice doing the quadratic formula. We got a equals 1, b equals 2, c equals 1. And so what we have is u equals negative b plus or minus b squared minus 4 times 1 times 1 all over 2a. What do we get? U equals 2 squared is 4, and 4 times 1 times 1 is 4. 4 minus 4 is 0. This is just negative 2 over 2, which equals 1. Equals negative 1. And where does that occur? Well, we got to sub back. U is actually sine x. So sine x equals negative 1. And that occurs when x equals 3 pi over 2. And every lap around, so plus 2 pi n. Pay attention to the signs. What happens if we made that right side positive 1? I get sine squared x plus 2 sine x. And when I move the 1 over, it's now negative 1. A is now 1, B is 2, C is negative 1. And my U, which equals sine x, is negative B plus or minus B squared minus 4 times 1 times C is negative 1 all over 2 times 1. Sine x equals negative 2 plus or minus 4. 2 squared is 4. Negative 4 times negative 1 is positive 4. This ends up being the square root of 8 over 2, which is negative 2 plus or minus 2 root 2 over 2. And I can split that up. I get negative 2 over 2 plus or minus 2 root 2 over 2, which is negative 1 plus or minus the square root of 2. And that square root of 2 is 1.414. So I get sine x equals 0.414 or negative 2.414. Now, just stop and think about it. Sine x caps. Sine x is stuck between negative 1 and 1. This one is actually outside the range of sine. So we use our inverse notation again. Now let's stop and look at the picture and see what happens. Remember, sine inverse is negative pi over 2 less than or equal to pi. Oops. Less than or equal to pi over 2. Actually, let me bring that back down and pause real quick and let you finish writing. All right. So this is the range of sine inverse. When it equals a positive value, sine is positive up here. So this is saying theta equals 0.427. Sine is also positive over here. What if I make this a reference angle of 0.427? I'm going to use my exact calculator value. That would make this angle right here pi minus 0.427. Pi minus answer. And I'm going to take the sine of this value and see if I get the answer. I still get the 0.414 that we had up above. So that one should work as well. Is ready to work with some more? Let's take a look at this example. Let's do tangent x plus square root of 3. Let's make that equal to secant x. So sometimes these are tricky functions to work with, but remember we had a relationship with secant squared and tangent squared had a relationship. What was it? It was when we started off with sine squared plus cosine squared equals 1, and we divided everything by cosine squared on both sides. And we saw that tangent squared x plus 1 equals secant squared. So maybe if I square both sides, I'll have a secant squared over here, a tangent squared over here. Let's see what happens. Let's take a look. I'm going to square both sides. And don't be hasty. Remember, this is tangent x plus square root of 3 times tangent x plus square root of 3. The right side is just secant squared x. I distribute. I've got tangent squared x plus 2 root 3 tangent x plus 3 equals, and I'm going to make that substitution in here real quick. Tangent squared x plus 1. Now I've got them down all to just one trig function. That's pretty nice. I'll gather my terms on one side by subtracting tangent squared x plus 1 from both sides. Minus tangent squared x minus 1. I get 2 root 3 tangent x plus 3 equals 0. I could, plus 2. 3 minus 1 equals 2, David. Get your math together. Let's move the 2 over. And when I divide both sides by 2 root 3, I get tangent x equals negative 1 over the square root of 3, which is negative square root of 3 over 3. Where does that occur on the unit circle? Well, (30 degrees is root 3 over 3. So we want 150 degrees, or 5 pi over 6. Or we want to go down 30 degrees. And this would give us 11 pi over 6. But remember when I said we were doing radicals, when we squared it, we might introduce extraneous solutions? We need to check to see if any of these are bad. Okay? I'll pause this, let you write it down a little bit while I get comfy in my chair, wiggle around a little bit. All right, let's check them. Now, my initial equation was tangent x plus square root of 3 equals secant x. And we said x equals 5 pi over 6 or 11 pi over 6. We're going to check them. X equals 5 pi over 6, plug it in. Your tangent of 5 pi over 6 plus root 3, does that equal secant of 5 pi over 6? Well, 5 pi over 6, this is negative root 3 over 3. And if I want to get a common denominator, I'll just multiply this by 3 over 3. I get 3 root 3 over 3. Does that equal secant of 5 pi over 6? This is 1 over cosine of 5 pi over 6. When you work that out, that's negative 2 root 3 over 3. And we add them together. 2 root 3 over 3, does that equal negative 2 root 3 over 3? No. So x cannot equal 5 pi over 6. Why don't you check the other one? I'll pause for a second. Please hit pause on your video while you work on these. Check that one. Okay. The tangent part actually doesn't change. It's still negative root 3 over 3. And we'll make that 3 root 3 over 3. Now this is related to cosine, and we're in quadrant 4, so the outcome is positive. It's going to be the positive 2 root 3 over 3. And when we work this out, we do get 2 root 3 over 3 on both sides. This is a valid combination. X equals 11 pi over 6 works, or any 2 pi times n multiple. The 5 pi over 6 was an extraneous solution. So when you square, check your answers. I do want to point out, let's go back to that equation real quick. We had tangent x plus root 3 equals secant x. And if I rewrite that, I've got sine x over cosine x plus root 3 equals 1 over cosine x. I don't want to multiply by cosine x. Because it may introduce some shady stuff. It may create bad juju. Like really bad. Like eliminate answers bad. And the reason why I don't want to do it, cosine x might equal 0. And if I multiply by 0, I destroy the equation. Now it turns out in this case, cosine x didn't equal 0. None of the solutions had. So I should have still gotten the correct answer. But you don't know when you're starting whether cosine x equals 0, which would be pi over 2 or 3 pi over 2, if that's a possible answer. I mean, you could plug it in and verify that neither side equals 0 and make sure that's a valid operation. But I think it's helpful to practice the other approaches. So let's discuss some pro tips. Pro tips. I've done a few of these. It's handy to check a couple things. Well, first off, try to decide if it's linear or quadratic. And quadratic has squared values, squared terms. It might help at this point. You might want to use a U-substitution. That's the official name for it. I kept using U because we do that a lot in calculus. Let U equal the trig function. And then the linear equation turns into a times u plus b equals 0 and solve for u. Quadratic, au squared plus bu plus c equals 0. Again, solve for u. And then replace u with the trig function. So in light of that, like b is literally, you can skip b, it's optional. If you're okay working with trig function, that's cool. So if it's linear, which means just one trig function and not squared, isolate the trig function. And find the angles that work. I'm going to call them proper angles, because that way I can fit it in one line. If there's more than one trig function, this is where, like, we had the cosine times tangent equaled cosine. Gather everything on one side and try factoring. Also under that vein, the last one we did had tangent and secant. You might try squaring and using identities. And finally, E. If it's quadratic, gather all on one side. And then factor or quadratic formula. Ready for more? Okay. Let's look at some examples. Let's see. I've got 2 cosine of theta over 2 equals 1. And let's do A is in 0 to 2 pi, B is all values. So normally when I have cosine x, I want x to be between 0 and 2 pi. But I don't have that here. I have theta over 2. So I'm going to replace that in here. I've got 0 is less than or equal to theta over 2 less than 2 pi. And if I get theta by itself by multiplying by 2, I have 0 is less than or equal to theta, which is less than 4 pi. So I actually need to check more solutions than just 0 to 2 pi. And the reason why is because this is a half angle. And it throws the bacon off a little bit. So let's see. Wait, something's not right. I'm saying this wrong. Let's try that again. I want 0 is less than theta is less than 2 pi. But that double or that half angle is screwing things up. All right, let's start this over. Okay. Normally I have 0 is less than or equal to theta, which is less than 2 pi. Let's say u equals theta over 2. So this becomes 2 cosine u equals 1. This means theta equals 2u. And I can replace that back in. I knew I was saying it backwards. Something sounded wrong when I said it. We divide by 2, and we see that u has to be less than or equal to pi. So we're looking for things in quadrant 1 and quadrant 2. So let's go back to solving this. I'll divide by 2, and I get cosine of theta over 2 equals 1/2. And this is really like cosine of u equals 1/2. Where does that work in 0 to pi? This is when u equals 60 degrees or pi over 3. But I don't want u, I want theta. So theta over 2 has to equal pi over 3, which means theta equals 2 pi over 3. Now, let's check. Let's look at that other angle, because this is pi over 3 here, but we also have 5 pi over 3. If I say theta over 2 equals 5 pi over 3, and I solve for theta, notice I get 10 pi over 3. 10 pi over 3 is greater than 2 pi. That one's outside the range, or outside the domain. For what we started with, for part A, 0 to 2 pi. So that's why we don't want that one. So that answered part A. Let me pause and let you write that down. Sorry for the confusion. I stumbled over my words a little bit. All right. Let's look at all. So we have 2 cosine. I'm going to rewrite the equation since I'm on another piece of paper. And I've got theta equals 2 pi over 3 is the solution. What is the period of cosine of pi over, or theta over 2? Well, this is kind of like saying cosine of 1/2 theta, which is like our cosine of b theta. And the way we checked period was 2 pi divided by b. So this is 2 pi over 1/2. I'll multiply top and bottom by 2. This will clear out the bottom. 1/2 and 2 cancel out. And on top, I get 4 pi. 4 pi over 1 is just 4 pi. So this has a period of 4 pi, which means that repeats, the theta that works repeats every 4 pi, not every 2 pi. So here we're going to have theta equals 2 pi over 3 plus 4 pi n. Now, let's go back to that. I want to give you another approach to look at. We had cosine of theta over 2 equaled 1/2. So this is backtracking a little bit. Another approach to take a look at. This is the same as saying theta over 2 equals cosine inverse of 1/2. Cosine inverse goes from 0 to pi. So the 1/2 values that work are right there, pi over 3 or negative pi over 3. Only that one's in the range. That's another approach of looking at it. So theta over 2 equals pi over 3. Theta equals 2 pi over 3. Hopefully that helps a little bit. Let's take a look at another one. Cosine 2x equals sine x. Now let's just look at 0 to 2 pi. Now cosine 2x has 3 forms. We could do cosine squared x minus sine squared x. We could do 2 cosine squared x minus 1, or we could do 1 minus 2 sine squared x. What do you think will work best here? Let's let the right side guide us. The right side has sine x. Let's choose the one that only has sine x, with only sine x. So if I do that, I get 1 minus 2 sine squared x equals sine x. I'm going to move everything over. This becomes positive 2 sine squared x. Sine x stays positive, and 1 becomes negative. If it helps, do a U-substitution. And we'll have 0 equals 2u squared plus u minus 1. That does factor. That turns into 2u minus 1 and u plus 1. And when I replace u with sine x, I have 0 equals 2 sine x minus 1 times sine x plus 1. We set each one equal to 0. If I solve here, I get sine x equals 1/2. And if I solve here, I get sine x equals negative 1. So if we look at our unit circle, 1/2 is at the pi over 6, which means I need a reference angle of pi over 6, which makes that 5 pi over 6. So x equals pi over 6, 5 pi over 6. And sine x equals -1 only happens in one spot, all the way down to 3 pi over 2. Let you write that down a little bit. Okay. One last problem, and then I want to talk about 7.7, which is extra credit for you. Let's take a look at, I've got 4 sine theta cosine theta equals -1. Now, I don't like that I have 2 trig identities in here. I really don't. Do I know any identities with sine theta, cosine theta? Where they're multiplied together? Well, there's those product to sum ones. Those are lame. But I do know sine of 2 theta is 2 sine theta cosine theta. So maybe I can rewrite that like this. If I make this 4 into 2 times 2, I can say that's 2 times 2 sine theta cosine theta equals -1. And I can turn that into sine of 2 theta. So I divide by 2, I've got sine of 2 theta equals -1/2. Where does that occur? 1/2 is a reference angle of 30, or pi over 6. And it's in quadrants 3 and 4. So this occurs at 7 pi over 6 and 11 pi over 6, right? That's where 2 theta equals it. I divide by 2 and I get theta equals 7 pi over 12 or 11 pi over 12. And since I shifted to sine of 2 theta, let's look at the period here. B equals 2. So my period is 2 pi over B, 2 pi over 2, which is pi. Which means every time we do another lap, another pi or a half a lap, we're going to hit the values again. So this is theta equals 7 pi over 12 plus n pi, or 11 pi over 12 plus n pi. A lot of solutions. So when you have different angles, half angles, stuff like that, you got to check the period, check how often it repeats. All right. that pretty much wraps up chapter 7. 7.7 is on solving equations that have trigonometric inverses in it. And you don't do that a whole lot. And in the interest of trying to keep things appropriate with us being completely separated by the coronavirus, I'm eliminating that section. It's still open, I believe, as extra credit on the homework if you want to give it a try. Let's see, do I have, let's take a look at our, this is our class setting. I've got files here. If you come into PowerPoints, you can take a look at 7.7. If you want to give it a try, it's worth checking out. Okay. But other than that, that wraps up chapter 7. We should be all completely caught up with what we have in the syllabus. I will make it so that I have a open Zoom class setting during our 2 classes this week. So let me bring this back up. What days do we meet? Monday and Wednesday? So let's look at the calendar. Monday the 30th, April the 1st. Those are our 2 classes before spring break. And April 1st. From 2 to 4, I will have a Zoom classroom open. Click on the link and join in to ask questions. Please try to watch these videos before then. Give these problems a practice try if you can. And we'll go from there. Peace.